So in this video, we're going to learn about inflection points. So hopefully you've actually watched the previous video about second derivatives and concavity. So let's review second derivative and what the signs mean. So in this cubic-like graph, let's figure out where the graph is concave down versus concave up. So from left to right, with this red thing that I'm drawing, this area here is concave down, meaning the second derivative is negative, meaning that the slope here, the slope is getting smaller. Imagine here, the slope of the tangent is maybe 5. Over here, the slope of the tangent would be, let's just say, 0.5. So the numbers are getting smaller. After that, we have in green, from left to right, this area here, it's curving up. So curving up means concave up, or the second derivative is positive. So now let's get to the definition of what an inflection is. Well, I don't want to read this. You can read this on your own, but an inflection point is the point where, number one, the point where the concavity changes from either concave down to concave up or the other way around, depending on what the graph looks like. In other words, this point here is a neutral point. It is neither curving up or curving down. So this second derivative, if you want to find the inflection point, first definition is when it's 0 or undefined, neutral. However, there's another definition of second derivative is where the concavity to the left and the concavity to the right are opposite. And number 3, an inflection point must be continuous. So meaning it is not a gap, it has to be a defined point. And not only is it a point, it has to be continuous with the graph at that point. So we're going to recap a bit about critical points. So when I speak about critical points, I'm talking about where the first derivative is 0 or undefined. So in this particular polynomial graph, there is no undefined tangent. There is no vertical tangent. So we're going to focus on where the slope is 0. So over here, we know that the slope is 0 at the turning points. All right. And also there's another point where the slope is 0, but it's not a turning point. Can you find it? It is right over around this area here, right over there. So I'm going to call this CP and CP for critical points where the slope is 0. Next thing here, we're going to figure out where the concave up and concave down. So I'm just going to use a different color. So start from left to right. So in this green here, it's like a parabola, like curving up until a certain point, and then somewhere around here, it starts to curve down. So it's curving down here. So I'm going to put here CD. Second derivative is negative. Over here in green, positive, curving up. And after this CP dot, it seems like it's also curving up. So in this case, second derivative is positive. So in other words, where are the inflection points? Well, by our definition, the inflection points are where the concavity changes. So imagine going from green to red or from red to green. Do we have those points, transition points? And yes, we do. Over here, this is considered a inflection point, or in this case where the second derivative is 0, neutral. And over here, it's just a coincidence that this dot here can be classified as 2 points. It's a critical point as well as it is a inflection point. So there are some points that can be classified as more than one category. So let's start with the algebra. So let's have a look at this function here. This function is the quadratic. We know this quadratic is facing down. Now, before we do the algebra, you can tell right away, no matter where you go, the graph is always curving down. So in other words, the second derivative is always going to be negative. So let's actually show this algebraically. So let's figure out the first derivative using the power rule. In this case, it's negative 4x plus 4. And let's figure out the second derivative. And if you notice here, using the power rule, the second derivative is negative 4. That means no matter what x value that you put in, the second derivative is always negative. Well, it makes sense because it's connected to the shape of the graph. This graph is always pointing down. So here we have a cubic function, and we're going to figure out where the inflection point is. So number one, let's figure out the second derivative. So we don't really need to work with the first derivative. We just have to move on to the second derivative. And if you notice here, second derivative is going to be 6x minus 3. So let's figure out the following. Let's figure out where the graph is concave up versus concave down. In other words, let's figure out the neutral. So let's set this to equal to 0. In this case, x is going to be 1/2. So over here, this is going to be a inflection potential point. I'm going to put a question mark here because sometimes the algebra may not prove that it's an inflection point just because you set the second derivative to 0. So what we're going to have to do is go with the second part of the definition. We need to check the concavity to the left or right, whether it's concave up and then concave down after this point or the other way around. So we're going to set up a second interval derivative chart. So this is called the second derivative interval chart to check for concavity. And what are we going to be using? We're going to be using this point here, this potential inflection point. And all we have to do is choose a number to the left of half, which is, let's choose 0, for example. If you take x equals to 0 and sub it into the second derivative, you're going to get a negative number. If you sub a number such as x equals to 1 into the second derivative, you're going to get a positive number. In other words, if I were to sketch the curve of this graph, this is concave down, and this is concave up. And by our definition right now, this point here, when x is half, can be classified as a inflection point. But there's one more thing we need to do. We have to make sure that there is a y value because sometimes the function may not have a y value depending on the restrictions of the function. So after you set x equals to find out that x is 1/2, you're going to have to sub in y. And I'm not going to do the work, but I can tell right away that there's going to be a value for y. So there is an inflection point. So here we have a very similar question, but this here is a irrational number. It's not a polynomial, it's an irrational function. So we'll do the same thing. We're going to look for the inflection points. So let's do the first derivative. That gives us 3x to the negative 2 over 3 minus 3. Then we go for the second derivative, which is going to be negative 4 over 9x, negative 5 over 3. So what we're going to do right now is, okay, let's figure out where the second derivative is 0 or undefined. And the reason why I mentioned undefined right now is because I can tell you right now that the x is located in the denominator, so negative 5 over 9, and this whole piece, if you want to show all the clear steps, it's an x in the denominator. So in this case, we have no x in the numerator, so we cannot find the zeros because remember, in an rational-like function, the numerator provides the zeros. So if I set this to equal to 0, I don't have a numerator to set it to 0 because negative 4, you can't write this out. This doesn't make sense at all. So I'm going to leave this out. So what we have to do right now is move on to the next neutral second derivative, which is where the second derivative is undefined. And when you look for undefined restrictions or of the denominator, you look at the bottom piece. In other words, I'm going to let x 5 over 3 is equals to 0. The 9 doesn't matter. X is going to equal to 0. So 0 is our potential inflection point. I'll put INF. I'll put a question mark. Let's see if it's a point first, because if you cannot get a y value, there's no point in going on unless I'm asking for where it's concave up or down. So let's actually see whether we sub in 0 into the x of the original function. And if you do that, we actually get a point here. We actually get negative 3. So we do have a point. So number one, I'm going to say inflection point, question mark. So we have an inflection point. We don't know yet. We need to go to the second part of the definition of concavity is we need to check whether after this point here, after 0, whether it's concave up versus concave down. So again, we do the second derivative interval chart, and we're going to use this second derivative. If you sub in a number to the left, such as negative 1, you're going to get a certain sign. You sub in a number to the right, such as 1, you're going to get a certain sign. In this case, to the right, I'm going to get a negative number, and to the left, I'm going to get a positive number. So what does that mean? So that means that this is going to be concave up. So I'll put a little swoopy up, and then this one here, concave down, I'll swoop it down. In other words, this thing here, this x0 is going to consider it is a inflection point because the concavity changes from positive to negative. So here we have a second derivative interval chart. To the left of A, we can see it's concave up, and to the right of A is concave down. The question right now is, well, what could this graph look like just based on what is given to us? So based on what we have here, a lot of students would draw the following: concave up and then concave down, and they would classify this as point A. They would classify this as an inflection point. That is correct. However, I did not give you any information about A, whether A is undefined, or is it is there a hole there, or is there an asymptote there, or is it like a jump? So in other words, we can open this up to different graphs. For example, I can take this graph here and break it up, make it a jump. So So make this, I'll put a hole here and I'll put a hole there, and there we go. I still follow the concave up and concave down. It's just that at A, which I didn't give you any information about, I can make a jump there, or I could close this dot because it's still a function. Or sometimes maybe I don't have to have the full curve. What that means is I can take this and make it look something like this. So in other words, I don't always have to curve down. I don't have to like follow the full curving down. I could just leave it as the following, sort of like a, this is actually a cube root type function. So these are just some examples, and I'm sure that you can come up with different alternative solutions for your graphs based on this condition. So based on this one here, this one over here, all right, this point here, you might think, oh, it's got to be an inflection point. There's a dot there, and there's change in concavity from left to right. But keep in mind, there's one more part of the definition of inflection point. It has to be continuous. Because there's a jump here, this is not considered a inflection point. So now would be a good time to pause the video and analyze this graph and see whether you can fill in the signs or the blanks in the following first derivative, second derivative, and the concavity. So let's look at the first derivative. So if you look at the derivative of this function here, where the slope is 0, we just look at the turning points. And at x is equals to -1, I know the slope is 0. Over here, it's also 0. What happens before? So the slope here is from left to right. Always read a graph from left to right. The slope is negative. From here to here, it's positive. But what happens at 0? Well, at 0, there is a vertical asymptote. So at 0, there is no slope. So I'm just going to call it not available. There is no slope at the vertical asymptote. Between 0 and 1, which is over here, the slope is positive, and after that, the slope is negative. So now let's look at the second derivative in terms of concavity. So look from left to right. So over here, the graph is swooping down and then up, so it seems like it is curving up. So from infinity all the way to the vertical asymptote, it is curving up. So I'm going to put here positive, 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 curving up, curving up, curving up. And afterwards, after the asymptote, it is curving down, meaning this concavity is going to be negative, curving down, curving down, curving down. Now what happens at the 0? I'm going to write down not available. There is nothing there. So not available, not available. So just to summarize what inflection point is, well, an inflection point in this case is going to be A, where A is accompanied with a point. So this is your X and the Y. That's number 1. Number 2 means this point here must be continuous. Number 3, the concavity to the left of the A and to the right of A must be opposite. So going from concave up to concave down, or from concave down to concave up. In other words, F prime, double prime, to look for this point, potential point, either has to be 0 or undefined, neutral signs. So now would be a good time to actually fully graph a ideal quote-unquote perfect cubic. So in advanced functions, you drew a cubic by looking at the zeros of the function. You didn't look at turning points or inflection points, but now in calculus, you're going to involve all those specific points. So let's actually look for I'm not going to go in specific order. I'm just going to go in order from first derivative. Let's find the critical points and classify them. So critical points, 3x squared plus 6x. Let's set it equal to 0. We don't need to set it to undefined. There is no denominator. We're going to factor things out. And we end up getting x is 0 and x is equals to -2. So let's classify them. You have a choice. You want to use a second derivative test or the first derivative test. And because we haven't done too much second derivative, I'm just going to take the second derivative. I'm going to have to anyways because I'm going to have to figure the inflection point. Let's take the second derivative of the first derivative, which is 6x plus 6. And now I'm going to classify these points. So let's actually sub in f of 0 into here. We get 0 times 6 plus 6, which gives me 6. What that means is this is going to be concave up because it's positive. And what that means is I can tell that at 0, at this critical point, it's going to be curving up. That means this is a local minimum. Let's test this one out. Let's sub in f -2 into this one here. If I did that, I get 6 times -2 plus 6. That gives me -6. It's going to be curving down. I know that at this point here, it's going to be a local maximum. So after I classify the critical numbers, I know they're points because I know that a cubic function is xcr and yer, so I know there's going to be an actual y value. So after finding my critical numbers, I'm going to solve for the y values, which is 0, 4, and over here I end up getting 8. So I have 2 turning points. The next thing we're going to do is find the inflection points, and based on the previous lesson slides, we're going to actually look at the second derivative, which we have already. So I'll put here 6x plus 6 and set it to equal to neutral. And this gives me x equals to -1. However, this is not guaranteed to be a inflection point. We need to check the concavity to the left and right. And also we need to figure out the y value, which does exist, which becomes the following, which is going to be 6. So let's do the second derivative interval chart. All right, so over here, let's set the second derivative and let's put the -1. Now in the second derivative, we do not need to include the critical points. We don't have to deal with anything from the first derivative, just from the second derivative. So we test to the left, choose a number to the left, you're going to get a negative. To the right, you're going to get a positive. So what that means is it is curving down, and then curving up. Therefore, we can say that this point here is a inflection point. So now we're going to actually graph in detail as much as possible. So I drew the 3 points. So I drew the critical points. So -0 and 4 and -2 and 8. So these are these ones over here. So these are the critical points. And this one over here in the middle is from the inflection point. So how do we bring them together in terms of the graph? So number one, we're going to actually curve. So in this case, I know that at 0, 4, it's a minimum. So I'm going to have to curve up from here to here. And the reason why I'm starting from the inflection point is because if the inflection point, it's curving up from the -1. Now from to the left, I have to curve down because it's a max. So I'm going to take the curving down and connect it to my inflection point. And we're not done yet because we do have to deal with the end behaviors. And based on what we know about cubic functions, we know that this graph to the right end behavior just keeps on going up, and this one here keeps on going down because they have opposite end behaviors. And there's our graph. And just to finish this off, I'm just going to label my points. I'm going to call this my local minimum, my local maximum. This is my inflection point. So when you draw an inflection point, make sure that your curvature, it's kind of obvious that the curvature is changing. So here we're going to deal with the irrational function, and we do the same thing. We'll look for the critical points and all the inflection points. So let's do this first derivative, which is 1/3 x -2/3 plus 2x. And we might as well just take the second derivative, put on the right-hand side, and that gives me -2/9 x to the -5/3 plus 2. So let's deal with the critical points, or the potential turning points, local max or min. In this case, I know that to find critical points, I have 2 choices to set it to equal to 0 or undefined. And the reason why I know it's undefined is because I know I'm going to have x in my denominator. So we're going to have to clean this up. So what I'm going to do with here is I'm just going to factor out the lowest common factor. In this case, they both have x's, and the lowest is x to the -2/3. So I'm going to factor x to the -2/3 out. I end up with 1/3 plus 2x, and I will get 5/3. If you're not too sure how I got 5/3, you just take this and divide everything by the common factor. And remember that if the bases are the same and there's exponents, what do you do when you divide bases that are the same? You subtract. So 1 minus -2/3 will give you this. All right, so let's actually put this into full rational form. So I'm going to put this here as 1/3 plus 2x 5/3 all over x 2/3. So now we're going to have to deal with the undefined portion. So I'm going to set f prime to equal to 0 as well as f prime to be undefined. Now when zeros, as I mentioned, it comes from the numerator. So I'm going to take 1/3, 2x 5/3 and equal to 0 and work it out. I'm going to set the denominator to equal to 0 and work it out. So I'm going to bring that -1/3 over and divide everything by 2. And then we're going to have to take the opposite operation of this. So instead, I'm going to take the 1/6 to the power of 3/5. And it depends on your calculator. Not all calculators can do this. If your calculator will give you, if it gives you an error, you're most likely going to have to do the following. -1/6 cube root bracket 3. So it really depends on your calculator. And you should end up getting -0.341. So now we're going to check whether these are turning points, local max, or min. I'm not going to like waste too much time, but there's going to be a y value for here. And also there's going to be a y value. If you take 0 and sub it back into here, the original, you get a 0. And if you sub in negative 0.341, you're going to get a number. And I think that's going to give us negative 0.58 something. Okay, so let's actually classify them. In this case, I'm just going to use the first derivative test since we did the second derivative test. So let's set up the interval chart for the first derivative test. So we're going to start off with our critical numbers, 3, 4, 1. And then we're going to get a 0. We do our test here. And then we know over here, I'm going to classify this. This is undefined because the slope is undefined here. The slope was 0, came from the numerator. And let's check. Anything to the right of 0 is going to be a positive. Anything to the left of negative, this is also going to be a positive. Anything between here, let's test a number that's like negative 0.1 is going to be a... And here are the signs. I had to fix this one up because it was wrong. So now if you have a look at our first derivative, we can say right now that based on this point here, this is a local, it's a local minimum because it goes down and then back up, and this keeps on going back up. So this point here is neither local max or local min. It doesn't turn. Let's look at the second derivative right now. So second derivative, we're going to do the same thing. To find the potential inflection point, we're going to have to clean up the denominator. So I'm just going to put the denominator in the bottom. So I'm going to have negative 2 over 9x 5 over 3 plus 2. But because I want things to be together, I'm going to put everything in terms of one fraction. So I'm going to have to balance this off with the common denominator. So in this case, it would be 18x 5 over 3. So now we're going to do the same thing, very similar to the first derivative, but using the second derivative, we're going to set it to 0, and we're going to set it to undefined because I have an x in the denominator. I'm going to set the denominator to equal to 0. I will end up getting 0. I'll set the numerator to equal to 0. In other words, negative 2 plus 18 x 5 over 3 is equal to 0. I'll clean it up. I end up getting, for example, 1 over 9. And then I take my calculator and I do the inverse operation, or some calculators can't handle this. They should be able to handle this, but you can put 1 over 9 cube and fifth root, and that will give you. And the y value, when you sub the 0.2 back into the function, you end up getting 0.2718. The next thing we have to do is, this may not be an inflection point. We have to show that the concavity changes, so we're going to look at the second derivative interval chart. And we're going to be using, also there's this point here. Make sure it's a dot here. We'll have to find the y value. You're going to sub it 0 back into the same function, and you get 0. So now we have two potential inflection points. Let's actually show this. So we're going to have to set up the potential inflection points, 0.27. And then we're going to do the interval chart using the second derivative, which is this one here. We're going to use this one here or this one here. You sub it in, and you end up getting the following. You're going to get a positive here, and then you're going to get a negative, and then a positive. So based on this, I know this is curving up, then curving down, then curving up. So we can conclude that these 2 points here are inflection points. So let's put this together. There's a correction I need to make. I believe that this here was wrong on my part. It should be 0.26-ish, give or take. So let's change this to 0.26-ish, give or take. And our y value would be something different. It would be 0.7. So you just have to be careful of the way that I put things in. You put things in your calculator, and me too. So this would be 0.7. So I just drew the dots. So I drew this dot here, I drew this dot here, I drew this dot here, and I drew this dot here. So now we're going to have to connect these dots. So I'll use blue. So I know that at 0.31, it is curving up and down. And I know that the concavity to the left of 0 is curving up. So I know I'm going to have to swoop up. And based on the inflection point, which is this one here, I'm going to have to swoop up like a parabola-ish. But what happens at 0? Well, we know it's an inflection point, but hold on. There's another thing that 0 is. 0 is undefined, and it's a dot. So what does a graph look like where it is a point, but the slope is undefined? It is a vertical tangent. So when I graph this, I'm going to accentuate the verticalness. I know it's a bit exaggerated, but just to show you that it is very vertical at that point. And afterwards, what happens? Well, I know that after 0, it has to curve down. Up to where? Up to 0.27, which is this, because this is also an inflection point. So I'm going to have to curve down. Curve down. Now, the question right now is, what happens after 0.26 or 27? It's going to curve back up. So this is the sketch. But there is a problem, because the way that I drew this, it seems like it is flat, right? The way that I drew this. Now, based on our first derivative test, is 0.26 part of our first derivative test? No, it's not. So that means that this part here, the way that I drew it, it cannot be flat. It must be positive. Well, why is the slope positive? Because, hold on, 0.26 is over here, and anything after 0 is positive. That means when I draw this part here, it has to be going up. So I'm going to have to redraw this a bit better. So here's my dot here. And when I curve, I'm going to start earlier, and I'm going to just do it like it's curving down, but it's not flat. It's still going up. So it's here. Notice here it's not like horizontal flat. It is actually slightly going up. And then after that, I'm going to have to, instead of curving down, I'm going to have to curve up. And there we go. And there is our graph.